Okay, good morning. I'm going to be talking to you about some future capability that will be present in FDS 6, namely that we've coupled a network HVAC model to FDS. So why do we want to do this? What was the motivation? One motivation was that we're seeing usage of FDS in places like data centers, where you have lots of cooling capability present to keep the computers from overheating, and typically these do a lot of recirculation of air inside the space. And they'll do smoke detection, for example, in the ducts, or also spot detection in the space. And so the ability to track smoke as it moves through the HVAC system, circulates back in, more smoke added, can improve your ability to model detection times. For atrium type, or other type smoke control systems, where you might have changes in the flow rate of exhaust or supply air based on pressurization of the space by the fire. Being able to model that behavior in the HVAC system can improve that capability. And smoke moving through ducts, to be able to have the ability to transfer contaminants or toxicants perhaps from the space with the fire to some distant compartment through an HVAC simulation. In FDS, the current version of FDS, there's some very simple capabilities that are present. You can define a vent with a fixed flow rate in or out. You can define some mass of species that come in through that vent. There's a simple quadratic fan model so that you can adjust the flow rate based on the compartment in the vent. But right now, there's no way for you to couple an inlet to an outlet. That is, I can't take gas out of one corner of the room and inject it in the other corner or anything like that, or have one fan connected to multiple inlets or outlets. So it's not a very full-featured HVAC capability. So one question that might occur is, well, we're doing CFD, just mesh the ducts and be done with it, right? Well, this would be very costly for a typical calculation. For example, if you wanted to actually resolve turbulent flow in a duct, you'd be needing to put 10 to 20 grid cells across the diameter of a duct. And in a room like this, with the length of ducts that you'd have in a space like this, that's just not affordable. And secondly, how in the heck would you ever validate that? You would have to show that for every one of your duct fittings, that your grid that you picked was reasonably representing the flow losses through that fitting, and that's really just not going to be something that's going to be feasible to do. Whereas we can look up in an ASHRAE handbook, a list of tables and figure out what that is, and use that as an input to a network HVAC model. So the basic solution approach is just a simple network solver. It's based on the solver in MELCOR, which is a U.S. Nuclear Regulatory Commission's best estimate code for containment safety. And we've done an indirect coupling to FDS, which I'll discuss what that means as I get into the talk. So basically what we have in MELCOR is a set of three equations. At every node in the equation, a node would be where one or more ducts join together or where a duct connects into a space. We solve for conservation of mass and energy, and then on the length of duct segments themselves, we solve for conservation of momentum. So we basically say that whatever flows into a node flows out of a node. We conserve mass. Whatever enthalpy flows into a node flows out of the node somehow. Conservation of energy. And momentum, what we have is we have a pressure difference. This would be the static pressure. We have a buoyancy term to account for elevation changes. We have a momentum source term, which might represent the fan, for example, and then there are flow losses, the fitting changes and whatnot that'll be present in the ducts. And what we do is we take that momentum equation and we just express that in terms of a finite difference in previous and last time step. One of the things we need to do is that as flows change in the system, as we remove or add air from a compartment, we change the pressure in the compartment. We need to account for that in our predicted velocities so that we don't get instabilities that occur. And the other thing that we need to account for is that this loss term for duct flow, it might be that if we're in a very sort of weakly driven term, like you have a compartment that's on fire and the ventilation system's been secured, so it's just the overpressurization of fire driving the smoke movement, that you can get flow reversal occurring in the ducts. And so we do sort of an expansion of the square of the velocity for the loss term to be able to account for flow reversal. So as I pointed out before, we got to account for the change in pressure over the time step where it's important. And this is sort of the simple schematic. Just illustrates that. Say, for example, this is our simulation space. We have 4 compartments that have doors open to some hallway, and we have two sealed compartments, right? As I remove air from this compartment, all these other compartments respond to that pressure change, whereas these compartments being isolated don't respond to the pressure change in these compartments. And we need to account for that in the solution scheme. That is, for compartments that are coupled together, we need to account for the change in pressures that result due to the airflows within the HVAC systems among those compartments. The way we do that is FDS right now has the ability through this an input it's called zone in FDS, where you can define a pressure zone within the model where FDS keeps track of the change of the bulk pressure of that zone. And this is how FDS does that. It integrates the divergence and the volume flow through the boundaries, and from that it determines what the pressure rise is of this volume. And so we can expand that term out, and that term has sort of two components to it. There's going to be a pressure change that comes just from the overall FDS solution. There's going to be a pressure change which results from the HVAC solution, and so we can express the previous time step prediction, subtract out the old HVAC solution time step solution, add in the new time step solution for the HVAC solution, and be able to predict what we expect the pressure to be as a result of the HVAC flows, and use that to try and keep things stable as pressures change within the system. So when we put it all together, we get this fully discretized momentum equation. So for every duct that's in the system, we'll have an equation, and that equation will contain along it terms for every other duct that is somehow coupled to that equation. And this then gives us a large linear system that we have to solve within FDS. And we always use upstream densities within the duct, so that as wherever the flow is coming from, the node upstream is used for densities. To couple with an FDS, we do an intercoupling. We don't directly couple the pressure solution of the HVAC solver to the pressure solution of FDS. Sort of computationally, that wouldn't be easy. It would probably add a lot of computational burden to FDS. And basically, the assumption that we make is that in a typical FDS calculation, the time steps are relatively small. HVAC systems don't generally change a large fraction of the air in a space over that small time step, so that the change in bulk pressure in the FDS solution due to the HVAC system is, should be very small in most cases. And so that allows us sort of this indirect coupling, where we express the wall velocity as the mass flow of the duct over the density and area of that vent. The density of the flow entering the space is a function of the species that are present and the temperature. For inflow, we just say the temperature is the duct temperature. The weight is the weight of the species at the wall, which then we have to account for both the advective and the diffusive flows, to get the appropriate boundary condition. And since we have that the velocity takes the density and the density takes the species, but the species also takes the density, sometimes we need to iterate on this to get a decent solution. But typically it's at most once or two times, so it's really not very expensive to do that, since in general, the values of the species don't change greatly in a time step, near the wall. So the solution method is we go through, after we've updated the species within FDS, we then go through and we update at all the locations where we said there's an HVAC vent, what's the average density and temperature near that vent that becomes the inlet boundary condition for the HVAC solution. We solve for the duct velocities, we update the density, temperature, and species at all the nodes internal to the network. We check to make sure that we've converged on mass and energy, and that the velocity solution's converged, and we will reiterate the velocity solution we haven't. And then if we have, we then go and we take the new values of the density and temperature and species that the HVAC solvers produced, put them back into these equations. That then becomes the boundary condition in FDS for the next time step. As I mentioned before, we don't do a direct coupling. We basically rely on the fact that the volume flow contributions of HVAC systems over a typical FDS time step are small. And so that the error in not doing and having this indirect coupling is small. I'm going to go through a couple of quick verification cases, a validation case, and then discuss some other capabilities that we're putting into it. So this simple case here, what we have is we have this green duct is injecting air into the system at 0.3 cubic meters per second. We have two inlets in the bottom, and in one case we have a loss of 16 in the duct for the red, and a loss of 4 for the orange duct. And if you look at this momentum conservation equation that we would expect to have, that the ratio of the orange to the red should be 2 in terms of velocity, and we see that the predictions are indeed that case, that the average flow through the orange duct is 2 and the average through the red duct is 1, giving us the correct ratio of speeds that we're. Second case is just a species conservation equation. So we have just a simple compartment. The The bottom half we initialize to a mass concentration of 1 of a species, and then the top has 0. And we see that at the very early part of the time step, so this vent sucks in and discharges here, and this green vent up here is an intake and then discharges through this yellow vent. So very early on in the case, we get pure, no species 1 being injected at the bottom vent and pure species 1 injected at the top vent. At some time later, when the slug moves across, we now get a mixture coming through the vent. And if we actually look at the mass of species 1 as a function of time, that mass is not changing, so we're not adding or removing mass. We're correctly solving the conservation equations. And this last case is looking at it's essentially sort of a similar combined solution. Now we have a case where we've got hot temperature on the left side and cooler temperatures on the right side. We impose a velocity at the top vent and the bottom vent. We're solving for the flow through the system by defining a loss. And what we should have is, since these vents are equal in area, once the pressure difference stabilizes between 2 compartments, the duct velocity should be equal. And so what you see here is that as the solution stabilizes out, that we have the same velocity top and bottom, which we expect, and that there's no significant change in the mass. You see this is the total mass in the system. So we get a little mass perturbation really early on, and this is mostly a result that this is a very coarse calculation that's being done, so it runs quickly. So there's some just numerical error in the mass transport scheme in those first couple of time steps that then steady out. If at a finer resolution, those would decrease. This next problem is a sample problem from the ASHRAE handbook. It's a sample problem number 7. So what it is just this hypothetical HVAC system. We've got 3 pieces of metalworking equipment where the filings are being collected by an HVAC system, so they can settle out in a dust collector and then be exhausted through the building. And the sample problem was set up to guide the user in how would you go about sizing ducts or fans. So we take the same flow losses and duct lengths that are used in the sample problem, and we solve with FDS to compare the pressure changes between these nodes with the ASHRAE solution. And we see that we have, we wind up with generally a % or so of the ASHRAE handbook solutions. And it should be noted that ASHRAE just presumes there's a fixed density in the ducts, whereas in FDS, since we have pressure drops, there's slight changes in densities along the space. So we'd expect some differences in the solution between the two, but then essentially we replicate these sort of hand calculation answers, sort of another just verification of FDS. Next couple slides, we'll be looking at the validation problem. This is occurred in a confined space facility. It was a set of tests that were done back in the 80s down in Mobile, Alabama. So we have a test facility has 23 compartments, 4 levels. There are 20 different openings between compartments. And we have 3 separate HVAC systems with a total of 129 components, a component being an unbroken length of duct or fan or damper or a connection to a compartment. So the 3 systems were a supply system that takes suction from a fan room and distributes to compartments. We have an exhaust system which takes suction from compartments and discharges to a fan room. And then there was a smoke control system which took suction from one specific compartment and discharged to the outside. And this is just a layout of the space, and we can see the 4 levels, and the different line types indicate the different HVAC systems. You can see it's a fairly complicated HVAC system. For a couple of test series, there are compartments on the 2nd level directly coupled to compartments on the 4th level by ducts that directly couple those compartments. We'll be looking at 2 tests. There's test 410, so it's 10th test in the 4th test series. It was a meter diameter diesel fire. So there's no HVAC, all the internal closures open. So this would be sort of an FDS simulation with no fans in terms of smoke movement. And then we have the 14th test in the 5th test series where we had a 0.7 meter diameter diesel fire. So for the first minute we have supply and exhaust fans running. These direct coupling ducts were present. There's 1 external closure opening. Most of the internal doors were closed, but they had ventilation grates in the bottom half of the doors, like you'd see in a lot of buildings. And then after 1 minute, the system was realigned, so the exhaust took suction from the outside, and the smoke control system discharged to the outside. So for this, all the HVAC losses are taken from ASHRAE table is based on as-built drawings of the facility. The fire size was based on load cell measurements under the fuel pan. There's a little bit of uncertainty in this data. This data was very noisy. So that's probably the largest source of uncertainty in these tests. And the fan curves were derived from manufacturers' data adjusted for the fan frequency that they're operated at during the test. A little bit of uncertainty into this process is exactly how the fans respond to the change in frequency. So what we have here is on the right side is this test 410, which was no ventilation system. On the right is a test with ventilation systems. We're looking at visibility in 2 compartments on the upper levels of the space. And what we see is that the dashed lines represent FDS, the solid lines represent the test data, and the colors correspond to the measurement locations. In general, we see similar behavior in FDS in terms of the rate of visibility decrease, though we don't always catch the arrival time quite correctly, but generally the rate of visibility decrease is matched. And then with the HVAC system, again, we see that we generally catch the time that the decrease begins, and the rate of decrease matches that was measured in the test. I think a lot of this uncertainty has to come with there's exactly when the fire is ignited, how quickly it grew in those early stages, which drives this arrival time isn't really well known from the measured data for the pan size. These next 2 look at velocities and then a couple of doors and hatches in the system. Again, dashed lines are FDS and solid lines are the measured data. And then sort of more importantly, looking at measurements made within the HVAC system. And we can see that in general that we're matching the velocities seen both during the 1 minute pre-burn period where it's the HVAC system's running, and then later on with the induction system running to an exhaust fan from the space, as well as with the exception of this blue duct, where we're generally matching pretty well the velocity seen in these direct couplings. Again, this is where we're solving for the flow based on the pressure difference between levels within FDS. Next couple of slides, just looking at some other capabilities we're in the process of adding. One is a filtration. Filters, obviously, they're especially a HEPA filter, which is important in semiconductor facilities or nuclear facilities where you're worried about capturing radioactive materials that might be within the facility. They're very prone to clogging from soot and preventing the HVAC system from maintaining a negative pressure, for example, within the building. Generally in filters you can express a flow loss as a loss of the filter when it's clean, plus some loss that's a function of the loading. And so a common approach is you just have a linear function, some constant times the sum of all the species loaded on it, where you can multiply a species by some factor. So maybe soot is twice as bad as condensed water, for example, on the filter, or you could have a more complex nonlinear function of loading. We've implemented filters as a special case of a duct node, so that basically, since we solve for conservation of mass at a duct node, all we do in the duct node solution for a filter is we take the filter efficiency and we compute a removal rate as the mass flow of the species through the filter times some removal efficiency, and we apply that as a sink term in the node mass conservation equation to remove the mass of the soot, for example. And so in this case, this is a simple case here. We have a compartment that's initialized initially to a 1% soot mass fraction. We have an HVAC system which takes suction out of this bottom red vent and injects it at this top blue vent, and it has 100% removal of soot through the space. And so here we see this green line is total mass of soot in the system, the blue is the mass in the gas, the red is the mass in the filter, and over time we see that we collect all the mass of soot on the filter, and we decrease the mass of soot in the space, and you see that indeed very early in the simulation we have no soot that's entering through this duct, and we slowly decrease over time the soot that's present in the space. So this is just a verification example. Another capability we've been adding is air coils, as the ability to do heating or cooling within the HVAC system. Currently there's 2 ways we can have to specify this. One is you can just give a fixed heat removal rate, and the other method is based on this sort of a heat exchanger efficiency type of calculation, where we can compute a theoretical maximum heat exchange, and that is where the temperature of the air and the working fluid are the same when they exit the system. So you can specify the properties of your coolant or your working fluid, its flow rate, its inlet temperature, and its specific heat. We compute this theoretical maximum heat exchange, and then you multiply that by an actual efficiency to get the actual heat removal. And then again, we apply this air coil as a component of a duct, And whereas when we go to do the downstream enthalpy balance, rather than just having rho U area H for enthalpy, we then subtract out or add, depending whether it's heating or cooling, the energy of the air coil to the solution before we do the node balance. In this case, we have a simple example. We have an HVAC system, sort of the same case, a suction in this red vent, discharge in the blue vent. In this case, we have a constant 1 kilowatt heat removal, and we see that over time, we reduce the temperature in the space. And if we look over a 40-second time period, we get, well, we're a fraction of percent low, but we get something like 39.9 kilowatts of heat removal from the system, showing that we are indeed getting this 1 kilowatt removal. Moving forward, some of the things we're looking at potentially adding are transient operation of dampers with position-dependent losses. Right now, they're just either fully open or fully closed. We're not doing anything right now in terms of condensation or evaporation of filters. The idea of maybe trying to do something for transient operation of fans, or to be able to account for motor speed, that is to have some multiplier of your fan curve to account for the speed you're operating the fan at. And then, lastly, one potential additional capability. This will probably be further down the road once we're sure that all the basic features are working. Would be to allow for duct wall heat transfer. So both to have a duct passing through a space to have heat transfer either to or from the space, or just losses within the system itself. And I'd be happy to answer any questions you might have.
Anybody have any questions? All right, Jason, thanks a lot.